In this lesson, we're going to continue looking at some laws of exponents. In particular, we're going to look at one called power of a power, and then near the end, we're going to look at just working with powers of 10 in particular. So we're just going to start with a little question. It says, Sandra thinks 2 to the 8 is equal to 4 to the 4. Is she right? Expand each to find out. Well, 2 to the 8 means 2. Let's do this in blue. 2 times 2, dot means multiplied times 2, times 2, times 2, it's 6, 7, 8. So 2 times 2 times 2 times 2 times 2 times 2, that's going to be 256. 4 to the 4, of course, is 4 times 4, 4 times. This one I'm going to break down and do it step by step so we can compare. 4 times 4 is 16, and we still have times 4 times 4. 16 times 4, so first I just multiplied those two together, now I'll multiply these two together. I'm just showing my steps. 16 times 4 is 64 times 4, and 64 times 4 equals 256. So yes, they are equivalent. So, interesting, 4 to the 4 is the same as 2 to the 8. I wonder if there's some way that we can use that later on. How about this? Simplify x to the 7 all to the exponent 3. Well, we know that this exponent 3 here, being on the brackets, is going to multiply the entire bracket times itself 3 times. So this is the same as x to the 7 times x to the 7 times x to the 7, right? So instead of doing x to the 7 to the exponent 3, we could write it out as 3 times x to the 7 3 times. But we also saw, using the exponent law for powers in the last lesson, that if I'm multiplying powers together, I can add the exponents. So this would be the same as x to the 7 plus 7 plus 7, which equals x to the 21. Can you see any connection between this exponent of 21 here and these two exponents up here? When we're doing powers of powers, so when we're doing multiplication of powers, we added the exponents together. When we were doing division of powers, we subtracted the exponents. What looks like is happening when we do a power with another exponent on it? Well, hold on to that thought. When you have an exponent raised to another exponent, we multiply the exponents. So if you predicted that, way to go, you're right. We can write that as a rule. If we have the base a, and we got this exponent m, but we raise the whole thing to another exponent n, then that's equal to the same as a to the m times n. Oops. So this is important to keep in mind. This is not the same thing as the multiplication one. Let me just go back to the multiplication one for a second. For multiplying, if we multiply two powers together, we add the exponents. And you'll notice that we have two separate powers. We got this one power here and a separate power here, power 1 and power 2 multiplied together. If I go back to what I just did, for powers of powers, we have a single power, a single base. We just have this a one time. We don't have a to the m times a to the n. We've got a to the m all raised to the exponent n. Not the same thing. So let's be really careful and not mix these up. So, one more time, if we're multiplying powers together, as we did in the last lesson, we add the exponents. But if I raise a power to another exponent, then I multiply the exponents. Confusing? Maybe. But if you work with it, then it quickly sorts itself out, but you do have to practice it. So, example, 3 to the 2 is equal to 3 to the 2 times 4, using that rule we just did, which is same as 3 to the 8. Let's draw that a little neater. 3 to the 8. Is that better? Maybe a little better. Why? Well, because 3 to the 2 to the 4 means 3 to the 2 times itself 4 times. And then using, again, the previous law from yesterday, that's the same as 3 to the 2. And we're multiplying all those powers together. We'd add the exponents, but that's the same as 3 to the 8. So that's why it's the same. Here's some other rules that we need to know. If you have a power of a product, the outer exponent refers to each factor inside the brackets. This is a rule that sometimes gets missed. People forget about this one, even in higher grades. This is a really, really important one. Or actually, both these bullets here are important. I'm going to put a nice red box around them just to make them pop out. Really important. So, what this one's saying is, let's look at this part. If I have, let's see, all right, just start with some new colors today. A to the m, and if I have b to the n, and I have an exponent p, that's equal to a to the m, all raised to the exponent p, and b to the n, all raised to the exponent p, which is the same as a to the m times p and b to the n times p as well. So sometimes my highlighting might not help at all, and if it doesn't in this case, ignore it. But the point is, think of it like I'm taking this p here and I'm applying it by multiplication, because it is a power of a power. I'm multiplying each of the exponents inside the brackets by that p. Okay? And then the one underneath is the exact same idea, except that it's given as a fraction to start with. So we have a to the m, we have b to the n, we have the exponent p, and again, we're just going to take this p here, and we're going to multiply it to the m and to the n. People always remember to multiply the m, the exponent m there, by the p. They never remember, or very often forget, to multiply the n. So again, notice how I got a to the m to the p on the top, which is what I often get, but I also have b to the n to the p on the bottom. We don't want to forget about this little p down here on the bottom. Often gets forgotten. So let's try some different examples of stuff. Express each of the following as a power with a single exponent. Okay, well, using our first rule, that's no problem. That would be 3 to the 2 times 5, which is 3 to the 10. If we do the next one in our head, it's going to be 5 to the 6 times 4. That would be 24. If we do x to the 3 times 7, 3 times 7 is 21. Express each of the following as a power with the base as indicated. Okay, you're going to see something like this in your homework. So when it says as a base of 5, it means rewrite this with literally a power with a base of 5. So 25 can be rewritten as 5 squared. Right? So just the 25 part can be rewritten as 5 squared. They're equivalent, but it still has the 4 on the outside. And then if I do the powers of powers rule, 2 times 4 is 8. So 25 to the 4 is actually going to be the same as 5 to the 8. If I do the next one, I'm writing as a base of 3. I could rewrite 27 as 3 to the 3. Again, these are equivalent. but it still has this 3 on the outside, and then using powers of powers, I multiply the two exponents and I get 3 to the 9. Those are equivalent. Now this is where it starts to get a little trickier, where you're going to see some examples here where I'm combining stuff. And that's what I indicated, I think in the last lesson, that each rule by itself is not hard. But when we combine them, then order of operations becomes important and things get a bit more confusing. So you need to know the basics, and then you'll be in better shape to do the ones as they get harder. So in this case, I'm going to do this first. So I've got x to the 8, and then I'm going to multiply that times this, that highlighted in green, and that's going to be x to the 12, because 2 times 6 is 12. And then I'm going to add the exponents together. And 8 plus 12 is 20. So just like in any other math, order of operations is going to play a role. Multiplying powers means we add the exponents. Dividing powers means we subtract the exponents. Powers of powers means we multiply the exponents. We know for order of operations that multiplying comes before adding and subtracting, and that's also true for exponents. That's why I had to do things in the order that I did. So I'm always going to do powers of powers before I divide or multiply powers. So again, in this case, I'm going to do powers of powers on these two parts first, giving me 5 to the 15 divided by 5 to the 6. Then I'm going to subtract the exponents. It's going to be 5 to the 15 minus 6, which is going to be 5 to the 9. And that's as simplified as we need to go. All right, in C part, again, let's stick with order of operations. So we know that brackets should come before exponents, so I should simplify what's inside these brackets first. So 4 to the 3 times 4 to the 7 becomes 4 to the 10 when I add those together. 4 to the 5 times 4 to the 1, don't forget there's a 1 assumed to be there, is going to be 4 to the 6 when I add those two exponents together. Everything is going to be, no, not everything. The top is raised to the exponent 2, the bottom is raised to the exponent 3. Now I have to do powers of powers. So I'm going to simplify the top. 4 to the 10 times 2 gives me 4 to the 20. 4 to the 6 times 3 gives me 4 to the 18. And the reason why I have to do the top and the bottom separately is whenever we're working with fractions, we do the dividing last. Think of it like the top is within its own brackets and the bottom is within its own brackets. Even if there weren't brackets, I need to totally simplify the top and totally simplify the bottom, and I always divide last. So now I'm down to my divide, and when it's powers, I subtract the exponents. It's going to be 4 to the 20 minus 18, which equals 4 to the 2. For this one, we've seen this rule before. Remember, I even drew arrows. I'm going to multiply 3 times the 4, which everyone remembers, but I'm also going to multiply 3 times the 2, which many people don't remember. So it's 6. Actually, there's 2 different ways of doing this, isn't there? Let's carry on with this one. I'll do it both ways. Since I started, I don't want to stop. So it'd be 6 to the 12 over 6 to the 6, and then I could subtract the exponents, and 12 minus 6 is 6. So that's one way of doing it. But then after I started, I realized if I follow order of operations, I could actually simplify the inside the brackets first. And 6 to the 4 divided by 6 to the 2 means I subtract the exponents. And I still have the 3 on the outside. And then if I do powers of powers, 2 times 3 equals 6. And I get the same answer again. So sometimes there's more than one way of doing something. Generally, I try to use order of operations, although occasionally I might miss something. But if I do miss something, it's a case where order of operations isn't going to matter in the end anyway. Here's a real tricky one, though. This one definitely is a trick. Not a trick, but a stumper for a lot of people. That goes back to that first bullet from up above. This 5, there's 2 parts inside the brackets. There's a 2 and there's an a squared. And this 5 has to multiply times the exponent of each. But wait, you say, there's no exponent on the 2. To which I say, oh ho, yes there is. It's assumed to be a 1, because we can always assume there's an exponent. So 2 to the 1 times 5 is 2 to the 5. And a to the 2 times 5 is a to the 10. Now, I could leave it like that. I haven't been simplifying any of my powers, so I could leave it like that. Any one of these numbers could be changed, or exponents could be changed to a number, right? 5 to the 9 could be put in my calculator. It's going to be a really big number, but it could be put in my calculator. 4 squared is easy. I can do that one in my head. That's just equal to 16. 6 to the 6, that's going to be a big number. I don't know that one off the top of my head. 2 to the 5, I do know that one. That's just 32. So if it doesn't tell us to totally simplify it, it's probably okay not to. Again, the wording should let us know which one to do. Here's one that puts a lot of stuff together. So again, you're going to have to keep your head clear and make sure you follow order of operations. And remember all the different rules. So first we're going to simplify. Then we're going to substitute in these numbers to simplify more. So when I combine this, x to the 4 and times all raised to the exponent 2, I get x to the 8. And maybe just to keep it in stages, I'm going to do only that in the first step. There's no rule, hard and fast rule, that you have to do certain steps, that you have to do steps the same way I do. Let's put it that way. I usually try to pick my steps that make it as clear as possible, though I fail sometimes, I'm sure. But if you show your steps slightly different and still make everything work out, I'm fine with that. Okay, so that's all I did so far was combine that part I highlighted in yellow. Now if I were to, now I got 2 different variables here with different bases. So if I do the x's in yellow and if I do the y's in green, and then we're dividing x to the 8 by x to the 5, we're going to get x to the 3, aren't we? We're going to subtract our exponents. And y to the 6 divided by y to the 3, again I'm going to subtract my exponents. So that's simplified. Then we get to the part where we do our substitution. So we're supposed to simplify first, then put 2 in for x and -1 in for y. So now I've got 2 to the exponent 3 times -1 to the exponent 3 as well. 2 to the 3 equals 8. So remember, a negative number to an odd exponent is going to be negative, and 1 times itself 3 times is 1, so that's still -1, and 8 times -1 gives us -8 overall. Okay, now we're just going to take a quick look at powers of 10. This won't take too long. Calculate the following without a calculator. So remember, when we're multiplying by 10 or 100 or 1,000 or dividing, we've already talked about how we can just move the decimal place, or in some cases, if they're big numbers, we can just add zeros. So if I multiply by 10, all we have to do is add a 0 onto the end. No need for a calculator, 240. If I multiply times 100, I'd add 2 zeros. Like, I'm going to skip down to number 3 here. So I can just add 2 zeros to the end. If I multiply by 1,000, I'm going to add 3 zeros on the end. So if I'm multiplying by a big number, just count the number of zeros and add that many, as long as it's got a 1 at the front. If I've got a decimal multiplied by a 10, then again, I'm just going to, I can't add a 0 on the end. That doesn't mean anything. But what I can do is I can move the decimal place 1 over for every power of 10 that we're going up. So this would be 456.1 when I move that decimal place over 1. And if it was times 100, I'd move over 2 decimal places. And if it was times 1,000, I could move over 3 decimal places. And I'm just going to add another one I'm going to call this 4a. what if I had 45.61 times 1,000? Well, I can move the decimal place over 2, but I'm supposed to move it over 3. So what I could then do is add a 0 onto the end to get that third decimal place. So if I did that, I'd end up with 45,610. So it's allowable to add zeros onto the end once you've run out of decimal places in a case like this. Dividing by 10, again, just imagine if you need to divide, if you need to have a decimal, you can always insert one. So 6 has an assumed decimal place there to the right of the 6, and dividing by 10, I'm going to move it one place to the left in that case. So that's 0.6, or just 0.6. You don't have to put the 0 up front. So I'm going to move it one place to the left for every 0. So this one, with 2 zeros, I'm going to move it 2 places to the left, which moves it from there beside the 3, where it's assumed to be, to the left of the 5. Now I'm going to move this one over 3 places. From there, 1, 2, 3, and so I've got 8.167. And this one that's already got a decimal in it, but I've got to move it 2 places to the left, it becomes there at the 8, so it becomes 8.452. So multiplying by multiples of 10, we move it to the right. Dividing by multiples of 10, we move to the left.